This lecture, we will see the differential equation for an orbit. In my previous class, we have seen the equation of motion and its first integral. In this class, we are going to see the differential equation of an orbit. In the case of a central force, we need to deduce the equation of the orbit whose solution can give us the radial distance r as a function of theta. Here I like to highlight one important point that we want to eliminate. Our ultimate goal is to eliminate the time dependence in the differential equation. That is, r is a function of time and theta also is a function of time. So we want to remove that time dependence and we want to make the relation that r depends on theta. That is our ultimate aim. In fact, our ultimate aim is we want to remove the time dependence. In my previous class, the previous class equation of motion, as I said, we have seen m r double dot minus L squared over m r cube is equal to f of r. Here, this left hand side second term is a centrifugal term. We know very well. Now we are going to see r dot. R dot is nothing but the time derivative dr over dt. So this can be written as dr over d theta multiplied with d theta over dt, which is equal to the first term you keep as it is dr over d theta, and the second one is theta dot. Now we know theta dot is equal to, already in my previous lecture in the first integral we have seen the equation of motion. L is equal to mr squared theta dot. Then theta dot is equal to, if you bring this mr squared left hand side, L over mr squared. So I have shown it in the green color font. So I am replacing theta dot as L over mr squared, of course, into dr over d theta. This is r dot. We have seen r theta is equal to L over mr squared dr over d theta. Um, then now you take r double dot. That is second order derivative of r with respect to time. That is just you multiply, sorry, you differentiate this again, that is d by dt into this entire term, because it's r dot. D by dt of dr by dt is r double dot naturally. So I have taken this as it is. Now our ultimate aim is we want to remove the time dependence. So that is our ultimate aim. So we know this relation, that is t by t theta uh, g of r, which is some arbitrary function which depends on r, into d theta by dt is equal to, that is, it is equivalent to tg over dt, tt over dt, t theta over dt. So which is equal to tg over dt. So make use of this relation. So r double dot become, I'm going to replace dg by dt equal to t theta. I'm going to use just this here. Here you can see t over t theta and g of r. Here g of r is this term, the red color font term. So L over m r squared dr over dt. Of course, this one I am keeping this t theta over dt, which is exactly equivalent to the d by dt of this g. This I am calling it as g of r, some arbitrary function. Now, theta by dt is equal to theta dot, and also we know theta dot is equal to, just now we have seen, L divided by m r squared. So I have replaced this, that is theta over dt, uh, sorry, theta over dt, uh, d theta over dt as m r squared, L divided by m r squared. Just to remove. Then r double dot can be written as this 1 over, sorry, L over m r squared I am bringing in front. So L over m r squared t by t theta into this L over m r squared t r over t theta. We have seen that r double dot is equal to 1 over m r squared t over t theta into L over m r squared t r over t theta. Now we are going to define u is equal to 1 over r. So, which implies the if you differentiate u with respect to theta, you will get this is, if you differentiate 1 over r, you will get minus 1 over r squared into dr over d theta, which implies if you bring this negative sign left hand side, minus du by d theta is equal to 1 over r squared dr by d theta. Now you take this expression r double dot. See the red color bond, r squared, 1 over r squared is equal to u squared. So I have replaced this. And you have seen that L over m, here also one L over m. So you take L over m outside, then this will become L squared over m squared. Of course, there is u squared here. T by t theta into 1 over r squared du by t theta. That is the rest of the terms which I have shown in the red color band is here. We have seen here 1 over r squared dr by t theta is equal to minus du by t theta. So I am replacing this, that is this term in the inside bracket. I am going to replace this by minus du by t theta. So naturally here there is one t by t theta outside. Here minus you can take outside. Then this is equal to t2u over t theta 2. Of course, there is a common term minus L squared u squared over m squared. We have seen that r double dot is equal to this one, this term. Now you take the initial equation of motion, mr double dot minus L squared over mr cube is equal to f of r. Now you change the variable. You know, m r double dot is equal to this one. This blue color bond you replace for r double dot. So I have taken that blue color bond one. Of course, there is a minus here. One m will come minus L squared, because 1 over R is U. So R 1 over R cube is U cube divided by M, this M, which is equal to F R. I am replacing 1 over U. Here you can see this M will get cancelled with this M squared. So you will get only M in the denominator. So this will become minus L squared u squared over m multiplied by T2u over T theta 2 minus L square u cube over m, which is equal to f of 1 over u. So we have seen this expression. Here you can see in first term and second term of the left side, you have common constant, that is L squared U squared over M. Here you can have you have L squared U squared into U. U cube can be written as U squared U divided by m. So now the common constant is common term is sorry common term is L squared U squared uh, over m. So inside the bracket you have T2u over T theta 2 plus u because it's a u cube here, so this will become u into u squared u cube. So this is which is equal to f 1 over u. So you bring this minus right hand side, you will get this term minus the f 1 over u will become minus f 1 over u. This is the that is this equation is the differential equation of the orbit, provided the force law f of r, which is equal to f of 1 over mu, in fact which is equal to minus uh, tv over tr, or here potential is known. So potential is when potential is known, this is the differential equation of an orbit. Conversely, if the equation of orbit is known, that is left hand side is known, then uh, you can work back up and obtain the Pohl's law f of r, like the orbital integral, which I have given in my previous lecture. The orbital differential equation describe the relation between the radial and angular coordinate of an orbit, a relation from which the variable time has been eliminated. So that's what from the beginning itself I am claiming this. That is, we are eliminating the time factor. Thank you very much for watching my videos and supporting me continuously. If you have any question, kindly send to the following mail ID vasumku@gmail.com. I will answer at earlier through email or through YouTube videos. My YouTube channel ID is youtube.com/at vasuvphysics. Thank you very much.